Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during this session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer each question at the end and to follow up with any unanswered questions by email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components, some of the related technology, and the extra design and engineering value that is added by a custom manufacturer such as Quantic Corry. To begin our session, I'm pleased to introduce Quantic Corry's Principal Engineer, Jeff Gibala. Jeff first joined the company back in 2015. He is an electrical engineer and holds multiple patents in RF technologies and medical devices. His passion, however, is finding solutions to challenging problems and helping customers meet their goals. So welcome, Jeff. Can you share an overview of your topic today and what objectives you have for the session?
Yes, of course. Thank you, Paul. I'm happy to be here today. So today we're going to talk about the different types of RF switches, some of the key parameters of isolation and insertion loss, the characteristics of the PIN diode, and switch architectures based upon PIN diodes, as well as the high power challenges with the switches, and then an example application. And then we'll wrap it all up with a summary.
Okay. Well, to get started, can you tell us a bit about the different types of switches you plan to discuss?
Yeah, so on this slide is a table of the different, comparing the different types of RF switches that are on the market. You know, there's a PIN diode, there's a FET switch that's based on transistors, and a mechanical switch that's much like a relay that has a moving, mechanical conductor that is controlled usually through a magnetic field. So in terms of frequency range, you know, a PIN diode is limited on the low side. It can work from, megahertz range up through 40 gigahertz, where the FET and the mechanical switch can work all the way down to DC as well as up through 40 gigahertz. The insertion loss, the mechanical is the lowest. It's better than the PIN diode and the FET. And from an isolation standpoint, all of the switches typically will get worse the higher you go in frequency. But the PIN diode and the FET will suffer a little more at the higher frequencies than the mechanical type. In terms of power handling, the RF power that you could put into a mechanical switch or a PIN diode can be into the kilowatt range, while a FET-based switch will top out in the 10-watt range. The switching speed, the time that it takes for the switch to turn on or off a port, the PIN diode and the FET are very fast. They can be down in the nanosecond range, while the mechanical's relatively slow compared to that in the 10 millisecond range. A PIN diode and a FET-based switch, in terms of life expectancy, is really infinite since they are electronic, while a mechanical one does have a finite life of typically specified in the 1 million cycle range. And then in terms of controlling them, they're bias circuits to control the switches. The PIN diode's fairly complex, while a FET and a mechanical switch are relatively simple to control.
Okay. Now, you had also mentioned isolation and insertion loss. Can you explain the differences?
Yeah, this slide here defines those terms a little bit. The isolation and insertion loss are two really important characteristics of a switch. And to explain these, I have a little application drawn up here that shows a switch being used to connect a common antenna to two different devices. So if this is a single pole double throw switch, it has a high power transmitter that can be connected up to the antenna through one path through the switch. And then it has an alternate path that the switch could be put into this alternate state and then would connect the antenna to some receiver. So high isolation will prevent the high power transmitter from RF energy coming from the high power transmitter from conducting into and damaging the high sensitivity receiver. And low insertion loss on the switch will maximize the amount of energy delivered into the antenna. So it will reduce heating of the switch and increase system efficiency. So isolation is defined as the ratio of the power at the off port relative to the power at the input port. And insertion loss is the ratio of the power at the output port divided by the power at the input port. And these are measured in dB, and they are converted to dB by taking 10 times the log of that ratio. And there's an example there that I have on the right. So if you had power in of 1 watt and you measured power out of 0.95 watts, and your off port had 0.001 watts in that state, then the insertion loss would calculate out to be minus 0.223 dB, and the isolation would calculate out to be minus 30 dB.
Okay, well, I guess that makes good sense. How about some of the characteristics of pin diodes?
Yeah, so on this slide, two very important characteristics of the pin diode which drive the insertion loss and the isolation are the resistance and the capacitance. So when a pin diode is forward biased, it looks like a resistor at RF frequencies, and this would be low value. So it could be an ohm, couple ohms, sub an ohm, depending on the specific device. And then when reverse biased, the diode looks like a very high value resistor in parallel with a capacitance. So the usable upper frequency is limited by the parallel capacitance because the high frequency energy can bypass the high value resistance through the capacitance. So obviously lower values of forward resistance and reverse bias capacitance are better. They will improve the isolation and return and insertion loss.
Okay, and can you also share some insights on various switch architectures?
Yeah, so this shows three of the basic architectures for pin diode switches. The first one is a series single pole single throw switch. So this operates by a series diode, and this diode is controlled by the bias circuits you see there to either be forward biased or reverse biased. So in the forward bias condition, as I mentioned before, the diode will look like a low resistor, and it will have some R forward bias resistance, and that will allow the RF energy to pass to the load there with some attenuation. Now, in the reverse bias condition, the diode will look like a high value resistor, as I mentioned previously, with a capacitor, and the capacitor will dominate, and the isolation will some of the high frequency energy can bypass that resistor through the capacitance, and the isolation will be proportional to the inverse of the capacitance, while insertion loss will be directly proportional to the magnitude of the resistance in this architecture. And another architecture is the shunt single pole single throw switch, where you have the pin diode in shunt with the RF path, and when it's in a forward biased condition, it's a low value resistance, so it reflects the energy back towards the source. And then when it's reverse bias, it looks like the high value resistance and looks like just the reverse bias capacitance, and the energy can pass through to the load. In this architecture, insertion loss is proportional to the reverse capacitance, and the isolation is inversely proportional to the forward resistance. So it flips from the series version. And this last architecture, this is the series shunt single pole single throw switch. And this architecture can be used to improve isolation because now you have two diodes that can be independently controlled. So in the one case where you're passing energy to the load, D1 is forward biased while D2 is reversed biased. And this creates an insertion loss that's proportional to the forward resistance of D1 and the reverse capacitance of D2. And then in the off state, you have D1 reverse biased and D2 forward biased. So it will reflect energy back towards the source. And that gives you an isolation that's inversely proportional to the forward resistance of D2 and the capacitance of D1. So these different architectures can be used to for very specific applications depending on what you need to solve.
Okay, I think I understand that. And how does all of this work to maximize isolation?
Yeah, so in order to diodes with low resistance and capacitance will provide the best isolation and lowest insertion loss. So there's a little graph here of the series shunt configuration. And this for any given for a specific frequency, as the forward resistance and the reverse capacitance increase, isolation will exponentially decrease. So the idea is to choose an architecture that will provide the desired isolation performance, and then the diodes that have the best, lowest forward resistance and the lowest reverse capacitance. And you can combine these different architectures to achieve higher isolation. So you could put 2 series diodes or 2 shunt diodes, and this approach will trade off insertion loss for isolation though.
Okay. And Jeff, does power range make a difference when determining which switch is best?
Yeah, power does. So there's really, we classify switches into 3 different power ranges. So there's a low power, which is typically a watt or lower. There's medium power, which is 1 watt to 10 watt kind of range, and then there's high power, which is 10 watts and above, and it could be up to kilowatts. There are pin diodes on the market that are suited for operation in these various ranges, and pin diodes switches, when designed properly, can operate at many kilowatts of power.
Okay. So I guess we should conclude then that the higher the power, the more complicated things get.
Yeah, that is definitely the case. Yeah, with higher power, you get added complexity. So one thing for sure is all the switch components, the connectors, the coupling caps, the diodes, the bias circuit elements, they must be carefully selected for operation at the operating voltages and the current levels of the signal passing through them. So, which can be very high. So take, for instance, a 1 kilowatt 50 ohm RF signal has a voltage waveform that's 316 volts peak and a current waveform that's 6.3 amps peak. Everything that signal is passing through or by needs to be able to withstand these voltages and currents. Now, with these higher RF voltage levels, they can actually act to bias the pin diode, which would allow the energy to in the off port, allow the energy to flow through the off port. So to prevent this, the bias circuitry must adequately reverse bias the diodes. And that could require your bias circuit to work at hundreds of volts, and all of its components have to, withstand these voltages. The switch operating conditions come into play. They have to be factored into the component rating. So, a VISWAR greater than 1 will increase the component operating voltage levels. Operating at higher altitudes will require the switch to have clearances to prevent voltage breakdown and will lower convection cooling. And components must remain within their temperature rating when including the operating ambient temperature plus the self-heating as they dissipate some energy from the RF that will cause them to self-heat. All of this has to be factored in and considered when picking out the components. And design trade-offs between insertion loss, isolation, power handling, and bandwidth are always necessary.
Can you maybe give us a few specific examples?
Yes. Here's a switch that we manufacture that this is a single pole double throw switch. It operates in the 1 to 1.1 gigahertz range, and it works at 5 kilowatts peak and 100 watts average. And this is a pin diode based switch, and it has very low insertion loss. It's on the order of I have a graph there. It's like 0.5 to 0.6 dB of insertion loss, and offers isolation of this one has isolation in the 65 dB range, so it's very, very high. One other thing about this switch is you can see it switches very fast. So 250 nanoseconds to transition the common port between output 1 or output 2. And it operates up to 85 degrees C, so it's up to the customer to supply enough heat sinking to keep this case no higher than 85 C in their specific application.
Well, excellent information, Jeff. Would you like to summarize?
Yeah, so to summarize all this, so I would say, pin diode switches can operate at high power levels with long life and reasonable performance. The series resistance and the capacitance of the diodes are key parameters that affect the isolation and the insertion loss. And then when you take a pin diode switch and use it at a high power operation, all the electrical components, they have to be carefully selected against the operating parameters. So, there's always trade-offs between the RF power handling, the bandwidth, the insertion loss, and the isolation. Those are all typical trade-offs that occur.
Okay, well, thank you. And could you maybe share some of the key differentiators associated with Quantic Corry in this area?
Yeah, yes, of course. Happy to. So, Quantic Corry, we offer high isolation, high power, and fast switching products. Whether you have an industrial application or an aerospace defense, we will have something to meet your needs. And we will also work with you to determine the right device for your application. Whatever your needs may be, your specific operating parameters, we can take those and recommend the correct device. And if we don't have a standard product, we can create a custom one from you. A lot of our products can be customized. If we don't have one, we can come up with a custom solution. So we're really a one-stop shop. And we can even take these switches and incorporate them into bigger systems, such as switch filter banks. So using our switches and filters, combine these into a common housing so that you have a complete solution. So we can offer you that as well.
Okay, well, thank you. And I think we have time for one question, and it's a simple one. I think you didn't really say very much about FET switches. Was there any reason for that?
Yeah, so the FET switches, they top out at about 10 watts, so they really don't fall into the high power classification. So we didn't really talk about those. We focused on the pin diode because it has the unique characteristics of high power, fast switching, good isolation, insertion loss. So that was really the focus that we were on here.
Okay. Well, thank you again, Jeff, and thanks to all of you for joining us. In conclusion, I think the bullets on your screen say it all. If you are a customer and have more questions, we'd love to hear from you, and we hope you'll call us on our engineering hotline. The number is on your screen, 724-940-7556, extension 276. Of course, there's no costs associated with these calls. And going forward, our next Tech Talk will be on Tuesday, January 9th, and the topic will be digitally tuned filters. Thank you, Jeff.
Thank you, Paul. Thanks, everybody.